the main concept that we talked about earlier is that for us to create a balanced trees, we are going to look at two different approaches. One approach is that we are going to treat it like a regular binary search tree, except that we rebalance regularly, and that is the AVL tree. And the second approach to do this is that we're going to impose a certain constraint to the structure of the tree so that we keep the balance property at all times. And we only allow the tree to grow in a balanced way. Now, there are mainly one mechanism to do that in terms of binary search trees, and that is red-black trees. Red-black tree is a binary tree. Now, but in order for us to understand the mechanism of red-black tree, it is useful to understand the mechanism of another tree that is called 2-4 trees. They are two highly interrelated concepts. Okay, so what we're going to discuss today is 2-4 trees. We hope to at least cover 2-4 trees, and then you go home and practice a little bit on the 2-4 trees, so that next week we're gonna come back to the red-black trees, and then at that point of time, hopefully you're already familiar with the 2-4 trees, and then that's going to allow us to illustrate the operations in a much simpler way. Okay, now the basic concept of a 2-4 tree is basically 2-2-4. So it's not 2 and 4, it's basically 2-2-4. Sometimes it's also called 2-3-4 trees. And the basic idea is that this is a multi-way search tree. Not binary, multi-way, meaning that you can go more than 2 ways. So in this case, right, it's going to follow the following definitions. Every node can have at most 4 children. So not 2 anymore, 2 will be binary, right? So at most 4 children, which means that you can have 2, you can have 3, you can have 4. Okay, so 2-4. Now a 2 node is going to have 1 key and 2 children. So this is a 2 node. It has 1 key and 2 children. Okay, a 3 node has 2 keys, 3 children. So this is a 3 node. 2 keys, 3 children. A 4 node has 3 keys and 4 children. These are the 3 keys and 4 children, right? So this is a 4 node. So a 2-4 tree is going to have a mixture of all these nodes. So you can have a 2 node, you can have a 3 node, you can have a 4 node, some mixture of them. Now, but there is an important constraint. An important constraint is that all the external nodes are of the same depth. So meaning that if you look at the nodes, right, you can only have external nodes only if it is at the leaf and nowhere else. So that is a condition for a 2-4 tree, which means that by definition, it is balanced. By definition, that means like without even trying very hard, right? It is a balance. Okay. Now, for the case, for this particular case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 internal keys. These are actual keys, right? And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 13 keys. We have 14 external nodes. Okay. Now, so in the general case, if you have n keys, you're going to have n plus 1 external. Okay. Now we're going to see how that happens, right? All right. So let's see. Let's take a look at the smallest possible 2, 4, 3 that you can have. The smallest possible 2, 4, 3 you can have is a 2 node. So in a 2 node, there is one value, 2 external nodes, right? So then this is true by definition, right? For a 3 node, so for a 3 node, so you're going to have 2 values, and you're going to have 3 external nodes. So again, true by definition. If it is a 4 node, well, I don't have to draw that, right? Because you have 3 keys, 4 children. So if you just have a single node, then this property is true by default. Now, let's say you want to grow your tree from a height of 1 to a height of 2, right? So let's say previously you already have a key, a node, right? And it has k keys inside, which means that it's going to have k plus 1 children, right? They're all external nodes. So they're all external nodes. So now at this point of time, it's true. Now we're going to look at it as if it's an induction, which means you're going to go from height 1 to height 2. So in this case, then, let's say I want to grow this, right? So I have k plus 1 external nodes. These k plus 1 external nodes are going to be k children, right? So it's going to be k children, k plus 1 children. So just like a 2 node here, it's going to have 2 children, right? So in this case, I have a k plus 1 node. It's going to have a k plus 1 children. So that means that previously I have k plus 1 externals that has now been replaced by pointers to actual children. But on the other hand, each of this child, right, is going to have one extra external node to its internal node. So if it has n here in values, then you have n plus 1. If this one has m, then you will have m plus 1. So which means that each of these children in the next level is going to contribute one extra external nodes. So which means that I'm going to have the new number of internal nodes will be the number of keys. I'm sorry, the number of keys is going to be the key that I find at every node, right? And the number of external nodes is going to be the number of external nodes I have on the children, right? And each of my k plus 1 children is going to contribute one more, which means that at the end of the day, so I'm going to have one more extra in the sequence of the children because it's going to consume one of them, right? So each of them is going to have one more, except so then the final one is going to have an extra one. So that means that at the end of the day, so I'm going to have a particular structure where even as I grow it, I'm going to introduce equal number of keys and external nodes with an extra of 1. So then this property is going to hold. Now, if we want to look at this in a more intuitive way, so let's take a look at this particular interpretation. So let's take a look at each of the external nodes, right? So this external nodes is going to encapsulate all the values that are smaller than the smallest value that I have on the tree. So because if I'm looking for 2, for example, I'm going to go all the way to the left, right? And that's where I expect to find 2. If I expect to find 1, I'm still going to go all the way to the left. I expect to find 0, I'm still going to go all the way to the left. So anything that is less than 3, I would have to find it through this branch. So this particular external node is for anything less than 3. Now, this particular external node is going to be between 3 and 4. So that means that I'm going to find anything that is between 3 and 4. Now, this particular external node is between 4 and 5. So which means that each of my external nodes is going to encode a particular range of values that are not yet represented in my tree. Now, if I have n keys, then I can have n plus 1 intervals in between my keys. Because if I have, for example, 5 keys, right? So let's say K1, K2, K3, K4, K5, right? So I'm looking at the spaces between my keys. So I'm going to have 6 intervals. So each of these intervals is going to be my external node. Okay, so now that is kind of the interpretation to this, right? Okay. And what we are going to do then is to make use of that property to see whether we can bound the height of the 2, 4, 3. Now let's first accept. Okay, so there's a typo here. This is actually not internal nodes. This is actually keys, right? So a tree of n keys has n plus 1 external nodes. Okay. Okay, so now if a tree has height h, then we want to know how many external nodes there could be. Well, we can define a range, because if I want the minimum number of the external nodes, if I want a minimum number, then I'm going to assume that all my nodes are 2 nodes. So that, you know, if I want to minimize a number, so for example, if I have a height of 2, then each one is a 2 node, then I only have 4, right? But if each one is a 4 node, then I'm going to have 16, right? So, but I know that I can go between the 2 extremes. Either everything is a 2 node or everything is a 4 node. If everything is a 2 node, then for the height of 2, so I'm going to have 2 to the power of 2, which is 4, right? If everything is a 4 node, then it's going to be 4 to the power of 2, which is 16. But in the general case, if the height is h, then I'm going to have 2 to the h here, 4 to the h here. And this is going to be the number of external nodes, which I know is going to be n plus 1, given that my number of internal nodes is n. Internal keys are n. So then if you take the log of this on both sides, I'm going to take the log 2. So then this is going to be h. This is going to be the log 2 of n plus 1. So for h, I'm going to take the log 2 of that. That's going to be 2h. So then from then on, we can see that we can now bound the height of such trees again to log n. So not log 2n, in fact, is a tight bound. So lower bound is log n, upper bound is log n. So then you more or less know that given a 2, 4, 3, the height of the tree is going to be in the order of log n. So then you can do searches in a very efficient way. Now, so then we're going to describe how to add a new node into the 2, 4, 3. And I'm going to describe it using an example first so that you capture the intuition. And then later on, you can look at the specific algorithm to do that. Okay, let's try to do what we do earlier, which is that we're trying to insert one number at a time. So let's say 1, right? So 1 will go in and create a new 2 node. So 1, 2 children, right? And then I have 2, no problem, 2. Then I'm going to create a 3 node. So then I just put 2 next to 1. I put in a 3. So no problem, still 1 node. But now it's going to be a 4 node. So 1, 2, 3, 4, right? Now I'm going to add 4. Well, just add external child again, right? So, but now I'm going to have a 5 node. So 5 node is bigger than 4 node, right? And we say that the limit is 4 node. Okay, why 4? We will come back to that question next week, right? So but let's say the biggest one is 4. Now, once we get to 4 nodes, we get a 5 node, and how has 5 children is beyond the size that we can accept. And therefore, we are going to split. So basically, we have a node that is too fat. So we're going to break it up into 2 sub-nodes, such that now we are going to introduce new ones. So since this is too big, and we can tolerate up to 4, so what we're going to do is that we're going to break it up. And because they are, so we're going to take the third key. We're going to take the third key, we're going to promote it to the parent. So then the third key is now going to go up to the parent. So if there's no parent, like in this case, we're going to create a new root node, which is just 3. Now, everything to the left of that is going to go to the left. Everything to the right of that is going to go to the right. Now, in this case, now I have a 3 node here. I have a 2 node here. I have a 2 node here. And now my tree has grown, right? And it's still a 2, 4, 3. Now, you can keep growing. right? So you can say, okay, why not 5? Okay, 5 is going to go in, right? How about 6? 6 is going to go in. So still valid, right? But once we put in a 7, now once we put in a 7, now it's now too big again, right? So we're going to do the same process. So 1, 2, 3, 4, take the third key, move it up. So now the third key is going to be 6, 3, and 6. So this is going to split. So then the new one, okay, so I'm going to have a bit busy here. So it's going to be 3, 1, and 2. 6, in the middle one is 4 and 5. This is going to be 7. So as we keep adding, each of the nodes that still has space is going to grow by a key. When it cannot contain it anymore, it is going to create a parent. And as we keep growing, we can keep splitting and growing upwards, which means that in this particular 243, we are going to grow by growing the root. So this is the opposite case as the binary search tree. Binary search tree, your root is the same, and you keep adding things by putting things below, right? In the case of 243, we're going to keep the property that is always at the same depth. So as you keep adding stuff, it's like making a pile. And as you create a pile, the thing grows upwards towards the root. Okay. Now, this is a pictorial description of that situation. So we're going to keep putting in a new value, a new key. Now, when it gets too big like this, we're going to split this, take the third key, move it up to the parent. So it gets promoted to be part of the parent. So then in this case, we're going to split. Now, as we split, we have a spare vacancy here, right? And we have a spare of 2 vacancies here, right? So then when we add new stuff, we now have empty space to add them up. So in that case, then we are going to do this, right? Now, okay, so there's a question on teams, right? Is the new parent always the third node? By convention, yes. So I think the idea here is that you want to split this in such a way that creates more or less equal vacancy on the left and the right, because you don't want to, you know, create the situation when it's already full and you're going to require another split soon. Now, by convention, you take the third one so that you have, right? It's just a big convention so that you fill things up from left to right, because the left is a little bit more full, so then you have a bit more vacancy on the right. But by convention, we pick the third one. Just like the way that we think about binary search tree, when we need to find a replacement, by convention, we go to the left and find the largest element. But actually, you can also go to the right and find the smallest element. Okay. Okay, why do we use a 2-4 instead of 2-3 and 2-5? Okay, that's a good question. So you can have a 2-3, you can have a 2-5, right? I think let's go back to this particular question when we talk about a red-black tree. So when we talk about a red-black tree, I think then it's going to get clearer as to why is it that we are dealing with a 2-4-3. Okay. All right. So as we saw earlier, right, we can split, and sometimes the split can cascade. The split can cascade. And in the case when it cascades, it means that, for example, you have a given tree, you add a new element. Let's say you need 17 here, right? And then 17 causes a split on the right-hand most node. So it causes a split so that 15 goes up to the top. So this gets split into 2, right? So now there are 2 here. But 15 going up to the top creates a too big a node here. So then in this case, it creates another split. So now we are essentially growing the tree by making it taller, creating a new root, and in exchange, we get higher capacity at the bottom to contain new additional values that are going to be coming in. Okay, for deletions, it's similar, but it's a little bit more complicated. Okay, so we're going to show it by example. Okay, there are 3 cases. They're actually quite intuitive, right? Now, the first case is when we remove something. Okay, so let me first make a point, right? The first point is that when you remove something from a tree, like a search tree, eventually you will be removing something from the bottom level. because what you need to do is that sometimes you remove something from the top or somewhere, and you have two children, you need to find a replacement. The replacement is going to come on the left and the largest one. And the largest one is going to be one of the leaf, right? Because, for example, if you're trying to replace 11, you go to the left, and then you have to find the largest one. It's going to be somewhere at the leaf level. Okay, so now we are always going to describe this based on what's going to happen at the bottom. So here, you remove 13 from a 3 node, so no problem. So because it just means that you shrink by 1, right? So then you get this one. So no issue, everything is okay. Now, the second case is that you remove something from a 2 node. So 2 node only has one key. You remove that key, now it becomes empty. So because it becomes empty, then we need to plug in the gap, right? And to plug the gap, we are going to look at the surrounding neighbors, and we're going to see, can we borrow a key from one of the siblings? If my siblings have spare, for example, this sibling has 6 and 8, so it has a spare of 1. Even if the sibling gives away 1, it will still be a valid node. But the sibling 6 cannot give directly to this one, because if 6, for example, goes to 4, where 4 is, then it's going to violate the search property, because 6 is now going to be smaller than 5, right? Which is not correct. So then the only way that 6 can give something is that 6 has to push 5, and 5 has to come down. So basically we push it away, right? So it becomes a transfer. So then 6 is going to go up, 5 is going to come down. Now this is going to be the new search tree. This particular case, we call it transfer, because basically we borrow from one sibling, and so the sibling contributes one key, it goes up, and then it goes down, right? Now the final case is what we call fusion. This is when your sibling has nothing to give you, right? So you remove 12, you find its replacement. The replacement is 11, so now we need to remove 11. But when we try to remove 11, 11 only has one sibling, which is 8. I mean, one immediate sibling, right, which is 8. So now in that case, 11 cannot take from 8, because then it will be empty, right? So what we're going to do is that we're going to merge. So we're going to take these two and merge them. But we cannot just merge, because right now there is 10 there. So for us to preserve the search property, the in order property, so then the 10 has to come down. Basically, we do a 3-way merge between the 2 at the bottom and one of the keys at the parent. So then it's going to create a 3-way merge to this stage, right? Sometimes you can create a knock-on effect. So for example, you take 14 up, you take 14 out, 15 has to come down and merge, right? Which is what happens here, but then it creates a vacancy here. Create another transfer. So then 11 has to come down, and then it's going to merge, right? So in that case, then you're going to create a shorter tree. So that is the case. Now you can kind of get an intuition of how the tree grows and how the tree shrinks. So it grows by creating more nodes, first sideways, right? And when you don't have capacity anymore, so you're going to go up. And then it's going to come down as you remove more and more values to this.